So back to where we were. Very, very quickly here. We're determining if the sequences converge or diverge by taking the limit as n goes to what? Infinity. All right, so we're on H. Any ideas on this one? It goes to 1? I would say that's probably a fair guess, because the negative 1 to the n on the top is just going to be a +1 or a -1, right? So these numbers, n over n, are growing at the exact same rate. The numerator, is it going to make a big difference if you have like a million plus 1 over a million versus a million minus 1 over a million? No. So your intuition should tell you that it's actually going to be 1, and it is, okay? So let's see if there's another way to determine that. You can do some of the strategies we did for integrations and stuff. You could split this up. N over n is 1 plus -1 over n to the n. And now it's going to be approaching 1 plus. Now what happens to the alternator, -1 to the n over n? This one is going to alternate signs, right? For n equals 1, it's going to be 1, or -1, sorry. And then it's going to be +1/2, -1/3, +1/4, -1/5. So this one, if you were actually to plot the values, it would be like this, that. So instead of having real numbers, they're actual finite dots. But what's happening to it? If you were to connect the dots, it would do something kind of like sine, right? And it would taper off and approach what? 0. And then 0 plus 1 is 1. So that's that one. Now, I do want to bring up something. Zach asked, how does sine and cosine get computed on the calculator? And I said I didn't know. It makes sense now. He looked it up. We're going to be learning in the next section something called Taylor polynomials. And Taylor polynomials are a way to express functions that aren't polynomials, like sine and cosine and e and the natural log and rational functions like 1 over x. We're going to be able to express those as polynomials. And the idea being that polynomials are a lot easier to evaluate than like sine, because polynomials are plug and chug, whereas sine is not, right? So sine of like 4, if you could write it as a polynomial, it's easier to plug in a 4 and evaluate it. And that's apparently how the TI calculators are programmed to evaluate sine, cosine, and my guess the same with E and ln. They're using Taylor polynomials. So we've had experience with Taylor polynomials this year when we've been writing equations of tangent lines, but there are polynomials of higher degrees that give you more accuracy. So I'm glad he looked that up. Be a good segue into the next section. But we're still in 9.1. So back to part I. A little mathematical aside there. -1 to the n over n minus 1 over n. If you got rid of the alternator, what would happen to that? Just get rid of the alternator. We call that an alternator, -1 to the n. It only affects the sign, not the magnitude. That's going to be n to the first over n to the first, right? So without the alternator, that would approach 1. So what happens when you add the alternator back in? It's going to be +1, -1. Or actually, it's going to start with negative when n is 1. -1, -1. I'm sorry, -1 plus 1. It's a long day already. -1 plus 1, -1 plus 1, -1 plus 1. What's going to happen? It's going to diverge by oscillation. I'm just going to write with a highlighter like I meant it. Diverge by oscillation. All right, letter J, 2 to the n over n plus 1 factorial. So here's where we could really start using that sequence or the family of functions and how they grow for large values of n. Who grows faster for large value of n? Exponential, essentially, in the top, or factorial in the bottom? Factorial. So this one should approach what? 0, and it does. So this is a convergent sequence, The terms eventually go to 0. How about this one? Oh my gosh, no kidding. The inside converges to 1, right? But the outside converges to infinity. So this thing converges to 1 to the infinite power. Is that a conclusive result? Oh, that's an indeterminate form, isn't it? And how do we deal with indeterminate forms? L'Hopital's rule. Yeah. So let's go ahead and write that as the limit as n goes to infinity of 1 plus 1 over n to the nth power. And because it's the exponential variety, remember that's where we set it equal to y. And we took the natural log of both sides. So now we get the natural log of y equals The limit as n goes to infinity. When I take the natural log of that, it becomes the natural log of 1 plus 1 over n. And, of course, to the nth power, what happens with the n exponent now? With the log in place, it slides in front, okay? And now if you plug in infinity, you're going to get infinity times the natural log of 1, which is 0. What's infinity times 0? No. Infinity times 0 is L'Hopital's rule. It's an indeterminate form, but it's in the product variety instead of the exponential. So now remember, all we had to do is bring one of those factors to the denominator. Which one do you want to bring to the denominator? Probably the n, right? It's a little bit easier. So we'll leave that in the top, and we'll call it n to the negative first on the bottom. And now when you plug it in, you get 0 over 0. 0 over 0 is a L'Hopital's rule format. So now we'll take the derivative of the top. How do we take the derivative of the natural log of blob? 1 over the blob, right, times the derivative of the blob. Well, the derivative of 1 is 0, and the derivative of 1 over n, which is n to the negative first, is negative 1 over n squared, negative n to the negative second. All over the derivative of the bottom, derivative of n to the negative first is negative 1 over n squared. So what happens with your negative 1 over n squareds? They divide out. And now we can evaluate what's left. What is the only n that's left? Well, it's right here in the denominator and the denominator. So what happens to 1 over n now as n goes to infinity? It goes to 0. And now we're left with 1 over 1 plus 0, which, of course, is 1 over 1. Is 1 the answer? Yes, Kevin. Oh, because 1 over n is the same as n to the negative first. So I did it in my head, n to the negative first. When you take the derivative, you get negative n to the negative second. Okay? And then I cleaned it up. Remember, that's equal to the natural log of y, so all we have to do is solve for y by doing what to both sides? E-ing. That's hard verb. E-ing both sides. So we get e to the 1, which is e. So there you go. This is e. This converges to e. And if you remember, this might be worth remembering. Remember, that's the definition of e to the first. 1 plus 1 over n to the n is the definition of e as n goes to infinity. If this were 1 plus 2 over n to the n, that would be e squared. 1 plus 3 over n to the n would be e cubed. So that is one of the many ways to define e. All right? And how about this one here, very quickly? That's a sequence. It doesn't have a sub n equals, but it's set off in braces. As n goes to infinity, we have a quotient. Which one grows faster? Top or bottom? The bottom. So this sequence converges to what? 0. Yeah. It converges to 0. Sweet. Okay, now you may have a question, a specific question on the AP exam that deals strictly with sequences diverging or converging. More than likely not specifically, but it does come up again when we start doing our tests for series. It's going to be the first thing we do. We're going to test for convergence of sequences, and I'll show you what that means later on. So it's still a very important skill, very similar to what we did with x, we're just doing with n, where n is a positive integers. Now, example 4, I debated skipping it. This is maybe something you won't even have to do on the AP exam, but it's kind of fun, okay? Intelligence tests have a lot of these on there. These are sequences, and your goal is to try to come up with, if it exists, an explicit form that helps you generate the nth term without doing it recursively by using the previous term. Okay, so I'm not giving it to you here. So if you notice 3, 8, 13, 18, there's 4 terms. That should be enough to establish a pattern. So the first thing you want to do is figure out how you get to the next number. Yeah, you would try kind of, the things you try first are, do you add or subtract the same number to get the next term? Yes or no? If no, do you multiply or divide it by the same number to get to the next term? Yes or no? In the first case, if it was a yes, it'd be arithmetic. In the second term, if it's a yes, it's geometric. After that, you're kind of on your own. There are other ways to generate recursive patterns and take the limit of those go to infinity, but that's for another day. So yeah, you said you add 5. And this is a pretty easy pattern. So anytime you add 5 to get to the next term, we call this an arithmetic sequence. And of course, how do you do repeated addition? Plus 5 plus 5 plus 5, we call that multiplication. So this turns into I'll just write it right here. It turns into multiplication. So it's going to be 5n, but then you have to do some possible adjusting. Minus 2. ... So that's one way to write the nth term. You can just extend the sequence plus yada, 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 comma, the rule of sequence, yada, yada, yada. Or you could just say it equals 5n minus 2. And then you can verify it works, okay? So we're starting with n equals 1, then n equals 2, so on and so forth. All right, the next one here. 5, negative 15, 45, negative 135. Times negative 3. Good. Now, anytime you're multiplying or dividing by the same number to get the next term, it's not arithmetic. We call it geometric. And geometric is essentially what we did with x's instead of n's. It's the same thing as exponential. They're really the same, okay? So if we're multiplying by the same number repeatedly, how do we abbreviate that? Abbreviated addition is multiplication, or repeated addition, I should say, is multiplication. Repeated multiplication is called exponentiation. So this is going to be negative 3 to the nth power, because you're multiplying by negative 3 multiple times, and then you maybe do an adjustment. So when n is equal to 1, we want to end up with a 5. So if I just plug in a 1 right here, I'm going to get a negative 3. That's not good. I want a 5. So what if I subtract 1? Because really negative 3 to the 0 power is 1. So if I subtract 1 from the exponent now, when I plug in a 1, 1 minus 1 is 0. What's negative 3 to the 0 power? 1. Now this is 5. It's your first term. Recall from exponentials, you wrote functions of this form, a times b to the x. And remember, a was your y-intercept, which meant it was your starting value, right? What value are we starting with? 5. So you can modify this by putting a 5 there. And let's see if that works. When n is 1, 1 minus 1 is 0. Negative 3 to the 0 is 1. 1 times 5 is 5. It works for the first one. Let's see if it works for the second. 2 minus 1 is 1. So we have negative 3 times 5, which is negative 15. When n is 3, 3 minus 1 is 2. You get negative 3 squared is 9. 9 times 5 is 45. Bless you. There it is. Okay? And this one, of course, would what? Converge or diverge? This one diverges. What would the first one do? It also diverges. They both get really big. Okay? So, again, you're not going to necessarily have to do that, but when you add to get the next term or subtract, it's arithmetic. When you multiply or divide to get the next term, it's geometric / exponential. All right, this one here, 1, 4, 9, 16, 25. It's plus 3, plus 5, plus 7. So it's not the same number each time. It is squared. There is something called common second differences. Watch this. This is kind of interesting. Plus 3, plus 5, plus 7, and then plus 9. Those are the first differences. What would be the differences in the differences? Well, that'd be a 2, 2, 2. When your second common differences are the same, it ends up being a quadratic. If your third common differences are the same, it's going to be cubic. So that's one way to do it, knowing it's a quadratic, or you recognize them as being perfect squares. Is there any adjustment to make besides n squared? No. I better do it like this. If we're going to write it without the a sub n, or as the nth term, we put typically braces around it. I'm going to skip D because that's the most challenging one. Let's do these first. We'll come back to it. 2 over 1, 3 over 3, 4 over 5, 5 over 6, 6 over 9. What would the next term be? 7 over 11. So this would be, again, the easy way. This is the recursive way. It looks like I'm just adding 1 in the numerator, and I'm adding 2 in the denominator. So if we're adding the same numbers both times, this is going to be some form of arithmetic. N plus 1 all over odd numbers 2n minus 1. Yeah. Basically, to get an even number, it's 2 times n. To get an odd number, it's 2n plus 1 or 2n minus 1. And that should work, right? Plus 1 plus 1 plus 1, so that's 1 times n. Plus 2 plus 2 plus 2, that's 2 times n. So again, repeated addition turns into multiplication, and then you can make little adjustments in the numerator and denominator. So that's correct. This one here, ln of 1, ln of 2, ln of 4, ln of 8. Well, I have a strong inkling it's going to be the natural log of something. So now we just focus on the numbers. 1, 2, 4, 8. Who do we appreciate? That's not how the cheer goes, which is why I'm not a cheerleader. Okay. Oh. It's not bad. Natural log of 1, natural log of 2, natural log of 4, natural log of 8. Who wrote this cheer? There's too many syllables. They're not that great. That would be the next one. How'd you get 16 from 8? Times 2. So it's 1 times 2, 2 times 2 is 4, 4 times 2 is 8. So that's the recursive way. You just multiply the argument by 2. How would we do that? Repeated multiplication turns into exponentiation. So it should be 2 to the n or 2 to the n minus 1 or 2 to the n plus 1. We just make an adjustment. Okay? When n is 1, I get natural log of 2. I want a 1. When n is 2, I get the natural log of 4. That's the third term, not the second term. So I'll do minus 1. Does that work? Now when n is 1, 1 minus 1 is 0, 2 to the 0 is 1. Got it. When n is 2 for the second term, 2 minus 1 is 1, 2 to the first. That works right there. Okay, now back to this one. This one's a little bit more challenging. From 4 to 10, you add 6. From 10 to 28, you add 18. So it's not going to be a common first difference. You don't really multiply by the same thing either, do you? Oh, yeah. Every time you add something new, you're adding a factor of that one. All right? From 4 to 10, it's a little more than 2. From 10 to 28, it's actually closer to almost triple.
Yeah, you're multiplying 2 times to get 10. And that makes it where the 4 times 2 is 8.
Is there any way that you could figure out what the next number is? Let's start with that. How do you get the next number? Times 2 plus 2?
And then if you do for the next one, times 2. Next number is plus 2 times the n minus 1. Because if you double 10.
If I double 10, I get 20 and add 8. So if I double 4, I get 8, I add 2. Yes, multiplying by 3 is a good way to get close to the number. 4 times 3 would be 12, but then I have to subtract 2 to get 10. 10 times 3 would be 30, subtract 2 to get 28. 28 times 3 minus 2. So this one's a little challenging. If you're multiplying by 3 each time, repeated multiplication should become what? Some type of exponentiation. And now we just need to adjust it. When n is 1, I get 3. I want a 4. How would I get a 4 from a 3? Maybe plus 1. Let's see if that works. When n is 2, I get 3 squared. That's 9. If I add 1, I get 10. When n is 3, 3 cubed is 27, plus 1 is 28. There it is. Okay? So you can start with the addition, or somewhere close, or the multiplication somewhere close. Addition becomes multiplication. It's arithmetic. Multiplication becomes geometric, we're going to call it, but it's really exponential, and then you adjust. So kind of challenging. Now, there is a way to do it recursively. Here's how you would do this recursively. You would say a sub 1 equals 4. That's your seeding value. And then you would say a sub n equals a sub n. Oops, sorry. You would take 3 times the previous term, which is a sub n minus 1, and then minus 2. And that works for n greater than or equal to 2. So this is called a recursive relation. With that little formula, it's like a programming language, you could then generate sequential terms. You start with 4, and then how do you get, this is the first term, how do you get a sub 2? Well, a sub 2 would be 3 times a sub 2 minus 1, which is a sub 1, which is 4, minus 2. And once you have that term, you have the a sub 2, then a sub 3 is 3 times a sub 2 minus 2. So that's how you write it as a recursive relation. But it does require the previous one. So the holy grail of sequences is, can you come up with an explicit formula for finding the nth term directly by plug and chug? If you wanted to find like the 57th term in this sequence, you wouldn't want to have to generate the first 56 terms just to get the 57th. Now we have a formula, you could plug it in. All right, so anyway, that's probably not something you're going to have to do a lot of, or if you do, it's going to be a pretty simple one. Let's jump to series now. The only difference between a sequence and a series is that a series, instead of having commas between the terms, has a plus sign or a minus sign. Okay? So a series is really the sum of the terms in a sequence. And so how do we show that we're adding the sum of the terms? We use the Greek letter sigma. So if I take like a rule of sequence, like let's just take this one right here, 5n minus 2. If I wanted to add those up instead of just list them, I would say the sum from n equals 1 to, let's see, 1, 2. If I just want to list the first 4, it would be, we'd read that as the sum from n equals 1 to 4 of 5n minus 2. So it's still important to have the rule of sequence, but by putting it behind a sigma, we are now going to say this is equal to 3 plus 8 plus 13 plus 18. And that would be a finite sum. If I wanted to know what the sum is from 1 to 4, there it is. If I want to know what the sum is from 1 to 14, I would just list out the first 14 terms and add them together. What we're going to be interested in, much like with sequences that go on forever, we're going to be interested in that question. What does that mean? What is the sum from 1 to infinity of all of the terms? So it's an important question to determine if a sequence converges or not, but it's an entirely different question and more difficult question to then determine if the sum of those terms converges or diverges. All right? Does the sum of the infinitely many terms converge and diverge? And this is very similar to then what we did with improper integrals, right? Where we had like a similar looking region that was unbounded by the horizontal asymptote, and in some cases the unbounded region was infinite, like you would probably expect, but in some cases it was finite because it went to the x-axis fast enough. So that's what we're going to be concerning ourselves with. Does an infinite series converge or diverge? One of the ways to determine if a series converges or diverges, a series, is by looking at the sequence of partial sums. That is, I'm going to find the first term, write it down. I'm going to find the sum of the first 2 terms, write it down. Find the sum of the first 3 terms, write it down. And if I do that enough times, I'll have the sums of, partial sums, I should say, of the first n terms, and I can see if the sequence of the sums converges or not. So let's look at this. Example 5. For a sub n equal 1 over n, and b sub n, a different sequence, to be 1 over n squared. Generate the sequence of partial sums. So I'm going to use capital S. Capital S sub 1 just means the sum of the first term. Capital S sub 2 means the sum of the first 2 terms. S sub 3, the sum of the first 3 terms. I want to see, basically, here's what I really want to know. The sum from n equals 1 to infinity of 1 over n, and the sum from n equals 1 to infinity of 1 over n squared. I want to see if the sum of the terms converge or diverge. Now let's look at the sequences themselves. 1 over n and 1 over n squared. Both of those, as n goes to infinity, they both go to what? They both go to 0. So both of the sequences converge. But what I want to know is if I start adding the terms in the sequence, does the sum converge or diverge? All right, so let's go ahead and start listing out some of the terms. The series from n equals 1 to infinity of 1 over n. If you start listing terms, when n equals 1, you get 1, and then plus, instead of comma, 1/2, plus 1/3, plus 1/4, plus 1/5, plus dot, 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 plus 1 over n, plus dot, dot, dot. So that's how you can also express a series. 2 ways to express a series. Number 1, you can write it in the collapsed sigma notation, or you can write it in the expanded sum notation, in which case the rule of sequence, as we saw with the series, or sequence, would appear somewhere down here. We still call this the nth term. Now my question is, do you think that sum converges or diverges? I start with 1, I add a half, then I add a third, I add a fourth. Converges? They're getting smaller, but I'm going to be adding something forever and ever and ever, even though it's by less and less and less. What approaches 0? what I'm adding approaches 0. So here's the kicker. There is a chance that it converges because, according to the sequence, there will eventually be a time where I'm adding essentially plus 0, plus 0, plus 0, right? Because 1 over n goes to 0. But we've already seen that in some cases, when we have an unbounded region for area, it can be finite or infinite. So the question is, do these terms go to 0 fast enough to make the sum of the terms converge? Well, that's what we're trying to figure out. Let's look at 1 over n squared. Let's expand it. When n is 1, we get 1. When n is 2, we get 1/4, and then 1/9 plus ... plus 1 over n squared. Now notice that 1 over n is going to be a larger sum than 1 over n squared, right? 1 over n squared has all the terms that 1 over n has, but also 1 over n has a few more, right? It has a 1/2 plus a third. Could that really make that much of a difference if both of them are going to be adding infinitely many terms? I don't know. So here's the first way to do it. Without any real, ingenious tests, we're going to look at the sum of the sequence of the partial sums. So let's do that. On the top one, what is the sum of the first term? I'm going to use a calculator for this. The sum of the first term is just 1, yeah? What would be the sum of the first two terms? What's 1 plus a half? 1.5. Yeah, I'm going to call it 3/2. Because it's a little bit maybe easier. What's the sum of the first three terms? 3/2 plus 1 divided by 3. Math, enter. You get 11/6. What's the sum of the first four terms? Well, to that sum, add 0.25. And if you math, enter it, so a calculator here can be helpful just to add fractions fast. You get 25/16. The sum of the first five terms, well, add 1/5 to that. And you end up with a 137/60. Do those appear to be approaching a finite number? Maybe the decimals are better. Let's do them in decimal form. 1.5, 11 divided by 6 would be 1.833. 25 divided by 12 would be 2.083. 137 divided by 60 would be 2.283. And let's just add one more. If I added the next term, it would be plus the sixth. That gives you 2.45. So this would be the sequence now of the first 1, 2, 3, 4, 5, 6 partial sums. So one way to determine if a series converges or diverges is to look at the sequence of the partial sums. If the sequence of partial sums appears to be approaching a finite sum, then you can infer that the series converges. Do these numbers appear to be tapering off towards a finite number? No. Remember, when that happens, usually it happens pretty quickly. They're getting bigger, like we would expect, but from 2 to 2.2 to 2.4, it's still leaping forward by 2/10 about. So the indication here is that this one grows infinitely large and equals infinity and diverges. If we did it for the next one, let's just do it very quickly. It's 1 and then 1.25. And then if I add 1/9 to it, I guess we'll have to pick up there tomorrow. What would your intuition tell you about 1 over n squared? You think it converges or diverges? If you remember from the integrals, 1 over x squared went to 0 fast enough. This one, we'll have to wait and see, I guess. See you tomorrow. The suspense.